Okay, so we are very happy to have Monica Pate today from Harvard for our 5th talk of this series. And she will talk about scattering amplitudes on the celestial sphere. So please, Monica.
All right, so thank you for inviting me to give this seminar over Zoom. So the general purpose of this talk will be to explain some new insight into the scattering problem in quantum gravity that arises from recasting the problem in a language that might naturally have arisen from a putative holographic dual theory. So the sort of overall motivation for this body of work is this central question: what is the holographic structure underlying quantum gravity in asymptotically flat spacetimes? And sort of the first step in trying to address a problem like this is to figure out what type of observables you would expect a holographic dual theory to reproduce for you. And in asymptotically flat spacetimes, a natural class of such observables are the scattering amplitudes. And upon recognizing that, then in some sense, there's an easy answer to the question, what is the holographic structure underlying quantum gravity in asymptotically flat spacetimes, which is that scattering amplitudes, the natural observables, are inherently holographic. So what do I mean by this? Well, so scattering amplitudes are answering the question, given the state of a system at a very early time, well, what will it be at very late times? And in doing so, this class of observables naturally live on the boundary. So more specifically, amplitudes are functions of the asymptotic data on past and future boundaries, which then we interpret as describing evolution to the bulk. But nevertheless, you might have imagined that you could answer the scattering problem without ever referring to bulk dynamics or time evolution at intermediate times. And by definition, a theory that answers the scattering problem in that way is holographically dual to quantum gravity in asymptotically flat spacetimes. So therefore, a reason for expecting that the holographic principle might apply to quantum gravity in asymptotically flat spacetimes is simply because the natural class of observables live on the boundary.
Sorry, Monica.
Yeah.
Could you speak up a little bit?
Yes.
Some people have a bit of trouble hearing, sorry.
Yes. Okay. So is this better?
Yes.
Okay.
Thank you.
So therefore, actually what we mean by this central question is this more precise formulation, which is there an intrinsically defined holographic dual whose observables can be interpreted as scattering amplitudes in asymptotically flat spacetimes? And one strategy for determining whether such an intrinsic construction might be plausible is to simply identify general properties of the holographic dual that are required by universal features of scattering amplitudes. And there are a number of examples of these universal features, such as symmetries, unitarity, universal behavior at high energy and at low energy. And today, what I'll be doing is I'll be presenting some results of a preliminary investigation into a collection of these properties. So a very natural place to begin is with the symmetries. And one reason for doing that is, in retrospect, this is in some sense the strongest evidence of an intrinsically defined holographic dual. And so, in particular, the scattering problem is constrained by infinite dimensional, sometimes known as asymptotic symmetries. And we now know that the constraints on scattering amplitudes due to these symmetries are equivalent to soft theorems, which are a known property of scattering amplitudes. And in particular, the sort of most interesting, or one of the very interesting examples of this is that the so-called subleading soft graviton theorem implies that the scattering problem in a theory of gravity admits a Virasoro symmetry. And so what one learns from this simple fact is that a holographic dual suggests that the holographic dual theory is a conformal theory in 2 dimensions. And this simply follows from the fact that the fact that the scattering problem mix of Virasoro symmetry is simply saying that the scattering data of the gravitational problem is organized by the 2D conformal symmetry. And more precisely, this means that we should be able to, in some sense, identify scattering amplitudes with 2D conformally covariant correlators. So in order to do so, sort of the first step is to understand what the origin of this 2D conformal symmetry is. And a sort of very simple way to understand why we found the conformal symmetry of a theory in 2 dimensions as a symmetry of scattering in 4 dimensions is that the 4D Lorentz group, SO3, 1, is isomorphic to the 2D global conformal group, SL2C. And since the idea was that this suggests that the scattering in 4 dimensions might be holographically dual to a theory in 2 dimensions with a conformal symmetry, well, in some sense, we want to be able to, uncover this 2D structure. And since the conformal symmetry was the foundation of it, we want to make the conformal symmetry manifest. And so sort of the most naive way you might go about doing this is to say that, well, dilations are a very simple signature of conformal transformations. So let's construct observables that transform simply under dilations in 2 dimensions. Now, more specifically, the observables we're interested in are, of course, the scattering amplitudes. So what we mean by that is we want to construct scattering states that diagonalize the 2D dilations. Now, standard scattering states are momentum eigenstates, and these diagonalize translations in 4 dimensions. But since we identified the conformal group in 2 dimensions with the Lorentz group in 4 dimensions, if we're diagonalizing dilations in 2 dimensions, which is part of the conformal group, then we should therefore be diagonalizing one of the Lorentz transformations. And so therefore the states that we're going to be interested in are related to the standard momentum plane wave eigenstates by a change of basis. So in order to figure out what type of basis transformation one needs to do, consider the following. So the first thing we want to do is we want to sort of figure out where the 2 dimensions are that this conformal symmetry, identify the 2 dimensions in which this conformal symmetry acts. And so we can do this in the following way. So suppose you have a massless particle which has a null momentum. Now we can always parameterize a null momentum by a net energy and a unit vector in 3 dimensions, which we can think of as picking out a point on the surface of a 2-dimensional sphere. And just by parameterizing null momentum in this way, we can canonically identify null momentum with points in 2 dimensions, namely points on this 2-dimensional sphere. But now, suppose we boost that momentum towards the direction x hat. Well, under such a boost, that acts on the momentum by just an overall rescaling, which I said by lambda. And what then you notice is that at overall rescaling rescales this unit vector. So we can note, so what we learn is that boosting a null vector that points in the x direction, in x hat direction, towards that direction acts as a dilation on this unit sphere. So therefore, if we diagonalize dilations in 2D, to diagonalize dilations in 2D, it's equivalent to diagonalizing boosts in this direction x hat. So how do we do that? Well, there's a sort of standard procedure for diagonalizing different transformations. And the first step is identify the generator, and the second step is find the integral transformation that diagonalizes it. So the example we're most familiar with is translations. And the generator then is just d by dx. And we know that this is diagonalized by a Fourier transform. This is why if we scatter states of definite momentum, we're diagonalizing translations. So similarly, now that we learned that the dilation in 2 dimension was supposed to be identified with this rescaling of the null momentum, we can identify the boost generator as this derivative operator. And since it's a little different than, for example, the translation generator, well, it's diagonal by a different integral transformation, which happens to be the so-called Mellin transformation. And so the upshot is that we can construct boost eigenstates that diagonalize dilations in 2 dimensions by Mellin transforming momentum eigenstates with respect to their energy. So just to reiterate, we take our momentum eigenstate, we parameterize it in terms of an energy and essentially a point on the sphere, and then we take a Mellin transform with respect to that energy. And what we get is we get states that are of definite boost weight as opposed to energy, and accordingly, the label of energy is replaced by a label delta, which is the boost weight. So now if you do this for every particle in your scattering amplitude, what you get is you get an amplitude of particles of definite boost weight, and these are referred to as celestial amplitudes.
Sorry.
Yes.
This boost eigenvalue, is
yes.
it like bounded below, like in CFTs, the dimension, or?
That's a great question. So what's known at this moment is that if you want to find a set of boost eigenstates that cover the plane waves, then actually this boost eigenvalue has to have its real part be 1 and its imaginary part take any real number. On the other hand, it turns out that if you're interested in studying things like, which in momentum space, sort of the avatar in this basis of soft particles in momentum space, so the things that generate the infinite dimensional symmetries, the asymptotic symmetries, those turn out to have integer boost weight, which are integer real valued boost weight. So it's still it's still sort of an open question about exactly what values you want this boost weight to take.
Okay, thanks.
Yeah. All right. So I just sort of motivated the construction of celestial amplitudes by saying that we should diagonalize dilations, which we could think of as sort of a simple signature of 2D conformal symmetry. But now that we've done that, we sort of want to ask, okay, these objects, how do they transform under a general global conformal transformation or equivalently a general Lorentz transformation? And to answer that question, well, the first thing is that often in studying 2-dimensional conformal field theories, it's nice to work with coordinates on a plane instead of coordinates on the surface of a sphere. Nevertheless, we can easily trade these points on the surface of the sphere for points on the plane by the stereographic projection, which is given by this formula here and depicted in this picture. Now we know that the action of the global conformal group on coordinates on the plane, well, it acts by Mobius transformations of this form. And what you then find is that under such a transformation, a celestial amplitude, which was constructed by these Mellin transforms, transforms according to this transformation rule. So what we see here is that, in fact, these boost weights play the role of the conformal dimension. And so previously, and in addition, if you have a particle with helicity in 4 dimensions, this turns out to correspond to spin in 2 dimensions, and that's the second value here. And so thus, by taking momentum space amplitudes and Mellin transforming with respect to the energy, what we find is we find objects that transform under the Lorentz group like correlation functions of primary operators in a 2D conformal field. So that's this transformation over here. So now that we've found a representation of the scattering amplitudes in which the 2D conformal symmetries manifest, let's start to incorporate some of the other universal features of scattering amplitudes. And in particular, we'll be interested in first kinematics. So we're going to be interested in Poincare, which is not just the Lorentz transformations, but in addition, the translations. Then we're going to look at what different universal behavior at high energies implies for these scattering amplitudes, and likewise different known universal properties at low energies, how these appear in these new bases. Okay, but let's do the easiest one first. So let's study these constraints, the kinematic constraints. And for concreteness and simplicity, let's consider the 2-to-2 celestial amplitude for massless scalars. Now, we already know from a couple slides ago that it transforms under the Lorentz group like a 4-point correlation function from a 2D conformal field theory. But what that means is now we can import some of the things that we know about 2D conformal field theories, which is that if you have a 4-point function, then the Z dependence is fixed by SL2C, or the global conformal group, up to an undetermined function of the conformal cross ratio, which is this combination of the points. So in other words, we can use Lorentz symmetry, or what we've reinterpreted as global conformal symmetry, to immediately deduce that the scattering amplitude must take this form. So this is accounting for the non-trivial behavior under the conformal transformations. And this you can think of then, so this is in some ways fixed by kinematics, and you can think of this is somehow the dynamical input. And here I've introduced H and H bar, which are the left and right moving conformal weights. But of course, because we're interested in scattering amplitudes, in things that can be interpreted as scattering amplitudes in 4 dimensions, there's an additional symmetry, which is the translations. And normally in a momentum basis, momentum conservation enforces the constraints due to translations. So to understand how these constraints appear in the celestial amplitudes, notice the following. So the first thing is that for 4-point scattering, all the spatial momenta are forced to lie in a plane. And this is just saying that, so the spatial momenta are 3 component vectors. Any 3 of them define a plane, and momentum conservation forces the 4th one to lie in the plane. Now this plane intersects the celestial sphere on a circle, which implies that these 4 points lie in the circle. And using the stereographic projection, one then realizes that mathematically, this constraint implies that this cross ratio must be real. So what we've learned further is that not only does the scattering amplitude have this sort of kinematic part, but translations tell us that this additional part that is unfixed by Lorentz transformations must be proportional to a delta function that forces the cross ratio to be real. And so that's to say that it's constrained by kinematics up to an undetermined function that depends on the real part of the cross ratio and the 4 external conformal boost points. But actually, if we think about this for a second more, it's a little disappointing, this result. And in particular, we expect Poincare to be more constraining. And the reason is thinking about what happens in momentum space. So let's recall what happens there. So momentum space, if you're studying 2-to-2 scattering, well then Lorentz symmetry tells you that the scattering amplitude, well 2-to-2 scattering of scalars, then the scattering amplitude can only depend on the Lorentz invariance, which you construct out of taking inner products of pairs of external momenta. But what translations further tell you is that in fact, only 2 of these invariants are independent. And so we typically take one to be, for example, the center of mass energy labeled by Mandelstam variable S, and the other one to be momentum transfer labeled by a Mandelstam invariant T. And so therefore, in momentum space, what one finds is that the scattering amplitude for 2-to-2 is constrained by kinematics up to an undetermined function that depends on only 2 parameters, the Mandelstam invariants T and S. So the natural question to ask is, does something similar apply into celestial amplitudes in this boost weight space? And so the first thing to notice is that, well, you can identify the conformal cross ratio, Z, with actually the ratio of these 2 Mandelstam invariants. So then sort of the question becomes, okay, well, what is replacing the overall energy scale that appears in these Mandelstam invariants, since the ratio can be identified with something we've already seen in this in the celestial amplitude. So to answer that question, the strategy will be to take this constrained form of the momentum space amplitude and simply take a Mellin transform of it. And so there's sort of a nice way to organize all the data, and that is, so previously we said that the ratio of the two Mandelstam invariants could be identified with the conformal cross ratio. So let's write them in this following way, where we've introduced this energy, this sort of center mass energy scale omega squared, and written the Mandelstam invariance in terms of omega squared and the conformal cross ratio. Now, this delta function is imposing momentum conservation, but we previously argued that actually momentum conservation on the celestial sphere tells us that that one of the constraints from momentum conservation is that the conformal cross ratio needs to be real. So one of the delta functions will impose that constraint. And then the other three can be written in terms of ratios of constraining essentially ratios of the energies. And finally, so this is the Mellin transformation, but we can rewrite this in terms of the overall energy scale that we used in these Mandelstam invariants, and then three ratios of energies. And so what we notice then is that these three integrals are localized by these three delta functions, so we should perform those integrals. And upon simplifying the result, what we find is this following decomposition. So we find that a 2-to-2 scattering amplitude for massless scalars has this first part, which is fixed by kinematics, and the second part is this object here, and that's capturing the dynamics. And this is particularly nice because what we found is that, in fact, the part in the part of a 2-to-2 celestial amplitude that is capturing the dynamics is actually very simply related to the part of a momentum space amplitude that is capturing the dynamics. That is, I take the momentum space amplitude, or the part of the momentum space amplitude that's capturing dynamics, I replace S with omega squared and T with minus Z omega squared, and I Mellin transform with respect to omega. And here, beta is up to an overall shift given by the sum of the external conformal dimensions. And so we've answered this question of what is replacing the overall energy scale, and that is that it is the sum of its conformal dimensions. Right, and so for the rest of the talk, since we're going to be focusing on properties of this dynamical part, because essentially that's the free part that is not fixed. Okay, so with that in mind, another property of scattering amplitudes is that, especially in a theory of gravity, we would expect them to admit an effective field theory expansion. So for this discussion, I'm going to introduce a specific example because I think it illustrates the general ideas quite nicely. So let's consider the scattering of massless scalars in momentum space that is mediated by a massive exchange in the S channel. So what we mean by an effective field theory expansion is that in momentum space, we can expand in small s, or s over m squared, and we find that the scattering amplitude can be written as some Taylor series. Now, let's consider the celestial amplitude for just the leading order term. Now, so essentially, this expression can be interpreted as marginally convergent if we take this parameter beta, which was related to the sum of the conformal dimensions, and make it imaginary, then we can interpret it as a delta function. But notice that as soon as we add any one of these subleading corrections, then we immediately ruin this marginal convergence. And in particular, it will always cause this integral to diverge in the upper limit. And so what we've just learned is that celestial amplitudes don't really exist for truncated effective field theories. And this is different than how we think about momentum space amplitudes, because in momentum space, we're used to what is sort of a familiar, what you might call Wilsonian paradigm, which is the idea that low energy physics is insensitive to the details of the UV. And we realize this explicitly by saying that if we're interested in studying scattering at low energies and we have a fixed tolerance for error, then we can truncate our effective field theory expansion and obtain a sensible result at low energies. But what we've just seen is that celestial amplitudes are always sensitive to this UV physics. And in fact, there was a drastic difference if we truncated the effective field theory expansion, and they really only, and so in a sense, they really only exist for consistent UV complete theories. And in retrospect, nevertheless, this UV sensitivity is simply a consequence of the fact that we're scattering boost eigenstates, which contain contributions from arbitrarily high energies, so are naturally sensitive to what's happening in the UV. So in particular, if we took this simple example and simply Mellon transformed the whole thing instead of trying to truncate at some order, then we get some nice simple result. So again, this illustrates this a fact that celestial amplitudes don't really exist for the truncated field theory amplitudes. But upon noting this, one might be a little bit worried because the idea was that this was supposed to help us learn something about quantum gravity, and one way to think about quantum gravity is through an effective field theory approach. And so one might be worried whether celestial amplitudes even exist for theories of gravity. And the answer is that in fact they do. And this is thanks to expected universal soft behavior at high energies. So basically there's a sort of, is there a question or?
Yeah, sorry, can I ask a question?
Yes, please.
I was curious in this scalar example. So eventually you can get some answers for this A, right? For this celestial amplitude.
Yes.
Did you explore if it has some like nice OP expansion or stuff like that? Like, can you check what are the operators that appear, stuff like that?
Right. So let me say, so in answer to the operator product expansion, yes, there actually turns out that, so let me see. So this idea of parametrizing momentum in terms of energies and angles, what this means is that in momentum space, if you have massless particles and they are taken to be collinear, then that actually sort of only affects this angular dependence, which is something that is not transformed when you go to this boost eigenstate basis. So collinear limits in momentum space are equivalent to OPE limits in this boost weight space. And collinear limits, there's some universal properties of those, so you can get sort of the leading collinear limits turn into sort of leading order operator products. Beyond that, there's been some preliminary work on doing something like a conformal block decomposition. And at the moment, there's been sort of various successes and various pitfalls, and the picture is not clear yet. I know that one thing that a group at Harvard is working on is there is a sense in which they appear to be able to take scattering of four massless scalars and find massive exchanges, which is fairly interesting because that means you're learning something about higher energy physics by scattering, massless scalars. That being said, it's also not entirely clear, right? The conformal block decomposition is something, it's not entirely clear what that interpretation is in the 4D sense, what that means to take apart a 4D scattering amplitude by a conformal block decomposition.
But should I think about these primaries that appear as some other scattering states, some bound states, is it?
Right, it's not clear. And
it's not clear.
Thing, it's not clear. And another thing to point out is that you might think that things that are like, resonances or unstable massive particles, well, if you just think I'm doing scattering and all my scattering state, all operators are associated to asymptotic states, which make it out to infinity, you may think, oh, I'm not supposed to include things that like decay or something. But these are boost eigenstates, and so that's another open question about whether if you're actually sort of integrating over all energies, those are actually now in some sense stable, good asymptotic states to talk about. So that's, yeah.
Okay, thanks a lot.
Mm-hmm. Right. Okay, so now I was going to explain why, in fact, there's a sort of general physical argument that saves us and tells us that, in fact, we expect in a theory of quantum gravity these celestial amplitudes to exist. And so the argument is as follows. So the idea is that actually one expects scattering amplitudes in a theory of gravity to admit a sort of universal behavior at high energies, or in particular at scattering much larger than this Planck scale. And that is because this scattering is supposed to be dominated by the physics of black hole production. So the idea is that if you're actually scattering at energies much larger than the Planck scale, then you should be producing black holes with order 1 probability. Now, of course, the probability for producing a black hole is given by a sum over the probability for producing any of those black hole microstates. And there are exponentially many of these black hole microstates where the exponential is the Bekenstein-Hawking entropy, which for scattering at center of mass energy omega is given by both IG and omega squared. And so what that tells us is that actually the scattering amplitude for producing any individual black hole microstate is exponentially small in Bekenstein-Hawking entropy. And likewise, this implies that the amplitude for 2-to-2 scattering, which is given by a sum over intermediate black hole microstates, is also expected to be exponentially small in the Bekenstein-Hawking entropy. So what that means is that this will imply that actually we expect these celestial amplitudes to exist. So specifically, I just argued that we should expect exponentially soft behavior at high energies in momentum space, and this ensures that this upper limit of integration will always converge. And so therefore, we sort of expect a signature of quantum gravity in the celestial amplitudes is that they're going to be analytic in this parameter beta, which I remind you is given by the sum of the conformal dimensions along the positive real axis. And indeed, we expect something different in quantum field theory. So in quantum field theory, one typically expects that at high energies, the scattering amplitudes admit power law fall off. So for example, suppose that the scattering amplitude falls off with power omega to the 2m. Well, then what one will find is that that celestial amplitude, well, it'll converge for beta less than 2m, and there will be a simple pole at beta equals 2m. So scattering amplitudes, celestial amplitudes that arose from a quantum field theory as opposed to a theory of quantum gravity, we expect to have poles at positive even integer beta. And indeed, if you look back at this explicit example, then we can see that there are indeed poles at this positive, at beta equal to a positive even integer. So, but nevertheless, we might wonder, okay, so while the celestial amplitudes didn't exist for truncated effective field theory action, we think that there's obviously physical meaning to the effective field theory expansion. So one might ask, well, can we recover this effective field theory expansion from the celestial amplitudes, or is that only a property of momentum space amplitudes? In other words, do we always have to transform back to momentum space to recover that information? And the answer is we don't. We can actually canonically extract this information directly from this boost eigenstate basis. And sort of the strategy for doing so will be to apply similar logic as we use to extract sort of the signature of the power law fall-off from power law fall-off behavior of quantum field theory amplitudes for celestial amplitudes. So in particular, if we had an effective field theory expansion in momentum space, well, we can sort of represent it as a sum over powers of the Mandelstam invariants S and T, which to go to the boost weight space, we want to replace with omega squared and minus C omega squared. And so we can write it as a power sum in this center mass energy omega squared. But now, if we look at what this implies for celestial amplitudes, well, we can essentially use this Taylor expansion, which is about, think of it as a Taylor expansion about omega equals 0, to study the contribution from the lower range of integration of this Mellon transform. And so what you find is that to each term in this power expansion, one has a simple pole at beta, and the residue of that pole is telling you the coefficients in this series expansion. So just to see it explicitly in our example, on the one hand, we could have taken this S-channel exchange and done an effective field theory expansion and learned that the coefficients of this expansion were minus lambda over m to the 2n. Now, on the other hand, we could have put it in boost weight space and then looked for the residue at negative even integer beta, and again, recovered the coefficients of the effective field theory expansion. So in other words, the effective field theory expansion is intrinsically still part of these celestial amplitudes and can be extracted in a canonical way.
Sorry?
Yes.
Do you expect this to kind of stop working at some point? Because when you get to very big beta, you are like in UV, no? So you have this exponential cutoff.
So it depends on how you are expanding your amplitude. So this power series sort of works to all orders. It turns out that like in this plane, let's see. In the beta plane, there's going to be sort of, so I just argued there should be sort of poles along the negative even integers. And this is the like leading term in small omega. And then as you go to bigger omega, you go this direction. If you recall how I described actually the UV behavior of the quantum field theory amplitudes, which also in some ways had a power series expansion around omega equals infinity, the leading pole would be, say, here. And the sub-leading ones, which go into the IR, actually extend in this direction. So the information gets repackaged just in a slightly different form.
Okay, I see. Thanks.
And the final thing to say is that actually, if you're studying scattering of massless particles and you did an effective field theory expansion about small omega, well, not only would you expect to find a power series, but you would also expect to find logarithms. And the signature of these in the celestial amplitudes can be seen by simply noticing that if you look at the contribution of a power of omega and the power of a logarithm of omega, then it actually just gives rise to higher order poles in beta. So once again, these the coefficients of these sorts of objects can also be canonically extracted directly from the celestial amplitude. Okay, and sort of the final property that I'd like to discuss is infrared divergences and their cure, both in, so I'll discuss them briefly in momentum space, and then also for the celestial amplitudes. So what is the statement? So the statement is that, let's consider, for simplicity, let's consider QED with massless charges. And what one finds is that scattering amplitudes in momentum space factor into a universal infrared divergent piece and an infrared finite piece. And this universal infrared divergent piece contains all the infrared divergences, and in particular, it's an exponential of a quantity that depends pairwise on the charges and momenta of the external particles. And because it's infrared divergent, I have, to write it down, I have introduced an infrared regulator being this capital lambda IR. Now, to sort of begin to understand its sort of avatar in loose weight space, a nice thing to do is to notice that since it was expressed as these, as in terms of pairwise momenta, that actually the angular dependence in this exponential can be represented as by a 2-point correlation function on the sphere. And then what one notices is that actually this entire infrared divergent part can now be written as a correlator of exponentials of this free field phi, which has this 2-point function. Now, why is this nice? Well, by actually writing the infrared divergent part in this form, then what one finds is that this statement of factorization into infrared divergent and infrared finite pieces can now be expressed as a statement pertaining to asymptotic states. So in other words, you can think of this factorization of scattering amplitudes as being a factorization of asymptotic states into this infrared divergent piece and some piece that reproduces the infrared finite part of the scattering amplitude. And this is simply because now we've rewritten this thing that which previously depended on pairwise interactions into something that's sort of a product for each asymptotic particle. But not only that, actually writing the factorization this way has some physical meaning. And that is that if we consider the transformation of this field phi, and we consider it transforming like a Goldstone boson, then what we find is that this vertex or exponential operator associated to each asymptotic state exactly gives the transformation of a charge Q state under the large gauge symmetry. And so that's just to say, under the Goldstone boson ascribed transformation of phi, this IR divergent factor fully captures the non-trivial transformation of asymptotic particle states under large gauge symmetries. So now let's put this statement on the celestial sphere. So this was so if we want to study what happens for celestial amplitudes, we take this factorized form. And now, since this exponential had two parts, it had one part involving this correlator of Goldstone bosons, and then it had another factor of omega, which is contributed here. And so in this sense, we arrive at a factorization of celestial amplitudes in terms of this correlation function of Goldstone bosons and this part where the dimensions have been shifted. Now, to understand why the dimensions have been shifted, this simply follows from the fact that if we know that if we have exponentials of free bosons in 2 dimensions, that those operators, even though the boson itself carries 0 conformal dimension, those operators carry net conformal dimension. So in particular, an operator like this will carry this sort of conformal dimension. And so therefore, this object transforms non-trivially under conformal transformations like a correlator of operators with this set of conformal dimensions. But we already know that the left-hand side has been constructed to transform like a correlator of objects with just simply the delta conformal dimensions. So this shift in dimensions is needed so that essentially the transformation of this entire right-hand side under conformal transformations matches the left-hand side. So that's what we've learned is that celestial amplitudes also admit a factorization, but this hard, and so where the soft part is now interpreted as the correlation function of Goldstone bosons for large gauge symmetry, and the hard part is just given by the Mellin transform of the original hard part with shifted conformal dimensions. And so the final thing I wanted to discuss is that in momentum space, one can construct infrared safe scattering amplitudes that in which this infrared divergent part has been removed. And the reason why this is a nice thing to do is that in fact, if one had studied scattering amplitudes with this infrared divergent piece and taken the infrared regulator to 0, then you find that all exclusive scattering amplitudes vanish. So if you're interested in the study of scattering amplitudes, it's nice if you're able to construct scattering amplitudes that are non-vanishing. So in momentum space, it was understood back in the 1970s by Pate and Coolidge that the way to construct such infrared safe scattering amplitudes was to dress charged states with clouds, coherent clouds of photons. And what they found is that you could dress a charged state with a cloud of photon of this form, where this function f is an arbitrary function of the momentum, provided that it satisfies the boundary condition that at q equals 0, it is equal to 1. Now, if one is interested in sort of a natural, if one is interested in celestial amplitudes, it's natural to choose this dressing or this function to be 1, so that such that this overall cloud of photons is the conformally invariant one. And what one finds by actually choosing this function to simply be given by 1, then if you rewrite this dressing a little bit, one actually notices that the dressing you can identify as involving photons in boost eigenstates with boost weight 1. Now, it turns out that in the study of sort of different photons of different sort of energy or boost weight, that it turns out there are actually 2 photon modes that have boost weight 1. One of them is the generator of the large gauge symmetry, and the other one is its symplectic partner. Now, since sort of well-established result at this point is that the soft photon theorem is equivalent to a Ward identity for large gauge symmetry, this is simply saying that soft photons are the generators of the large gauge symmetry. And by using logic similar to what we use to deduce the signature of the effective field theory expansion for celestial amplitudes, one can also realize that the generator of soft photons, the generator of the large gauge symmetry, which is this soft photon, is related to a, it is actually equivalent to a photon of boost weight 1, where you've picked out a pole in its boost weight. So the reason why I'm telling you this is that, so this was the generator of large gauge transformations. It was one of the boost weight 1 photons. And I said that there were 2. And in particular, the one that we found in the dressing that gave us infrared finite scattering amplitudes is this other combination. But nevertheless, so you can use sort of a standard mode, creation annihilation, commutation relation, and momentum space. And using these 2 different expressions, you can find that essentially the generator of the large gauge transformations and this other delta equals 1 mode in the dress, which appeared in the dressing, that they are symplectic partners. And therefore, so the natural symplectic partner of a generator is the Goldstone boson. So the upshot of this is that we're able to identify the delta equals 1 photon that appears in the dressing that constructs for us infrared finite scattering amplitudes with this Goldstone boson. So that's just to say here that if we take this dressing, we choose the conformally invariant one, that at the end of the day, we're able to identify this combination of photons appearing with the Goldstone boson of the large gauge symmetry. And simplifying everything, one finds something like this. And the reason why this is interesting is that this is precisely canceling the infrared divergent factor that we previously found from factorization. So putting that together, what one finds, yes?
So this is a bit like in standard holography, which you have like a gauge field in the bulk and you have a constant current on the boundary. Here you have the photon in the bulk and you have the holomorphic current derivative of phi on the celestial sphere, something like this.
Yeah, so zero modes of the gauge field in the bulk are currents on the boundary.
Okay.
Yeah. Right. So what one learns from this is that there's in this new basis, there is a sort of natural infrared safe construction of scattering amplitudes, which is that you dress charged particles with these boost weight 1 photons. It precisely cancels the infrared divergent correlator of Goldstone bosons, and therefore you find that the dress states, which you knew were infrared finite to begin with, are actually just equal. The dress amplitude, which was infrared finite to begin with, is just equal to this hard part of the amplitude, which was given by the Mellon transform of the hard part in momentum space with these shifted dimensions. Right. So now a similar story can be told in gravity, and that is that again, in momentum space, it factorizes into an infrared divergent and infrared finite piece. The infrared divergent piece is slightly different, but you can recognize essentially that this is the same as it was for the charge as in the QED, and now the charges have simply been replaced by the momenta. And similarly, one can interpret the angular dependence in terms of a correlator of fields and rewrite this infrared divergent piece in terms of a correlator of exponentials. And once again, interpret the factorization of amplitudes as a factorization of asymptotic states, where now the piece that gives rise to the infrared divergent part of the scattering amplitudes is the piece that is charged under supertranslation symmetry, which is the analog of the large gauge symmetry, and the piece that gives rise to the infrared finite part of the scattering amplitude is the supertranslation neutral part. And sort of the final sort of non-trivial generalization is that actually if one considers what happens for celestial amplitudes, then, so this was the factorization in momentum space, but now notice that these exponentials, unlike in the case of QED, involve the energy, and the energy was something that is no longer a quantum number in the boost weight space. So the way to think about this is that in momentum space, you have this operator P, whose for momentum, which momentum space states diagonalize, and so they have the eigenvalue eta, which is a sign telling you whether it's an in or an out state, and the energy. But in boost weight space, this can be interpreted. So we have it act on the momentum space one, it returns eta omega, but then we see that that extra factor of omega shifts delta by 1. So in other words, this operator in the boost weight space, the boost weights are no longer diagonalizing this operator, and instead it shifts the dimension of these operators by 1. So what we've learned is that the infrared divergent part for gravity is now not just a factor, but actually an operator that acts on this infrared finite. And finally, one can again obtain infrared safe scattering amplitudes in momentum space by dressing with clouds of gravitons. And there is a conformally invariant choice, which can be identified as an exponential of this Goldstone boson, which is the Goldstone boson of supertranslation symmetry. And so one again arrives at this conclusion that the dressed states, which were infrared finite by construction, are the dressed amplitudes, which are infrared finite by construction, are actually equivalent to this hard part of scattering amplitude, which is just the mallotransform of the hard part in momentum space. Okay, so let me summarize. So I began by sort of motivating and reviewing the construction of celestial amplitudes, and this was simply simply represent the scattering of particles in boost eigenstates as opposed to standard momentum eigenstates. And the reason for studying such objects is that they transform under the Lorentz transformations, like correlation functions of primary operators in the 2D conformal field theory. And then we went on to study a number of universal properties of 2-to-2 celestial amplitudes. And so what we found is that, for example, translation symmetry implied that there was only these amplitudes only depended non-trivially on the real part of the conformal cross ratio and the sum of the conformal dimensions of the external operators, which we denoted by beta. Now, an effective field theory expansion in 4 dimensions implied that the 4-point function in other words, the celestial amplitude, had poles at negative even integer beta. Now, the soft UV behavior due to black hole production in momentum space then told us that we would expect in the theory of quantum gravity that the 2-to-2 celestial amplitude be analytic for positive real beta. And then the final part was that I described how soft factorization in momentum space into an infrared divergent and infrared finite piece could be interpreted as a current algebra factorization of these celestial amplitudes, and that upon dressing scattering states with clouds of photons or gravitons to obtain infrared safe scattering amplitudes, that this was interpreted as dressing with Goldstone bosons of these to obtain infrared safe celestial amplitudes. And so sort of the outlook at this point is that there's many additional properties of scattering amplitudes which are universal that remain to be fully understood in this new language. And conversely, I think it's also interesting to investigate sort of the implications of different more standard properties in conformal theories for scattering amplitudes in 4 dimensions. So thank you.
Okay, well, thank you very much for the nice talk. And okay, I'm gonna pause the recording.